Hello, my name is JAlfieri and I'm in EC 311, 331, and 341. Today for the KI presentation 2, I'll be talking about the audio backend of a speaker. To start out with, we assume that the system is an LTI system, meaning it's linear time invariant, to simplify and be able to do calculations. We assume that there's a signal that's put into the system and then there's an audio amplifier to be able to change the audio so that when it is released out of the speakerphone you can hear it. When you put in a certain frequency, that there is a frequency response of the system, and determine that frequency response both has a magnitude and phase part of it. Say for example your frequency spectrum of your frequency response shows that you'll have a DC component and whatever your frequency F0 is. Let's say for example it's at 1K, you'll see in the spectrum that you have a slight dB magnitude at that frequency. Now if we consider real life, most signals that we have are non-linear signals. So therefore we have spillage over when determining different parts of the signal itself, where when you linearize it, Taylor series, we truncate the rest of x squared and above. But now if we consider x squared, x to the third, x to the fourth, and whatnot, a lot of those frequencies overlap with each other so that you therefore have new harmonics at different frequencies. Now let's say if you change your input signal from a sinusoid to a square wave, how would you figure out what V out is? So if you were given a certain frequency response, you would then therefore try to find the Fourier series coefficients of that frequency response. And through that you will be able to see at what frequencies the harmonics come out. And depending on the magnitude of it, you can consider when to truncate such harmonics where you no longer have a gain anymore. Say like a company decides to build a new processor, well, they're going to consider up to a certain amount of harmonics before the gain becomes insufficient and therefore can truncate the rest of them. Now moving on to the 331 section of the KI presentation, we'll be talking about the audio amplifier itself and the circuit that composes of it. As you can see, there are two amplifier MOSFETs within this circuit itself. The goal of these MOSFETs is to amplify the signal. One thing to note is to see what would happen when you bias the transistor in such a way to change the gain. As you can see, if you bias the transistor to 0.7 volts and you compare it to if you bias it to 0.65 volts, you can tell that there is a different gain as seen in this curve up here. A way you can tell from the circuit's perspective is to look at the signal analysis of GM and R0. GM is proportional to the differential of ID over VGS, while R0 is the differential of VGS over ID, and this is proportional to 1 over VGS minus VTH squared. So if GM is increasing by a set amount while R0 is decreasing by a squared amount, this will make the overall gain, which is a function of both GM and R0, actually change. Another thing to consider is what would happen if you change the actual input voltage that is going into the system itself. As discussed in 311, this will end up creating nonlinear segments of the frequency response. If you look at the output sinusoid that you should get, you can see that the bottom parts of the graph is being truncated. And there is no one sinusoid that is linear that can create this. Therefore, you know there are nonlinear components within the signal itself. Finally, we want to consider why we have two stages of an amplifier in the first place. You'll see that R out is a function of both RL and R out. And because of this, if the load itself, the speaker, is small, then most of the gain that is being generated by the amplifier will be dropped across R out, which we do not want. To fix this, we'll add another transistor. And what this transistor does is changes the output impedance. By doing this, you can see that the transconduction of the second transistor is a lot larger. So that if you do the R out equation, you can see that most of the drop would be across the load itself, which that is what we want in a speaker. And one thing to note as well is if you calculate the gain using both transistors, you'll see it is slightly less than the gain of one transistor alone. But by changing the output impedance, more of the overall gain is being dropped across the load itself, which we want. So it's kind of a balance between how much gain you're losing over how much is actually being dropped over the speaker itself. And finally, we'll be going over the 341 magnetics part of the KI presentation. This part mainly goes over the actual speaker itself and how magnetism is used to create the audio waves themselves. There is a cone with a coil in the back with a permanent magnet within it. This coil wraps around the magnetic core and a current is thrown into it. This creates a magnetic field that it oscillates, and depending on what way the permanent magnet switch creates the speaker to move back and forth itself. This creates the actual audio waves themselves. You wouldn't want to have a heavy material for the speaker cone itself that moves because a lot of energy would be lost to it. Looking at the hysteresis graph, we see itself that the permanent magnet only stays at one point because it is stationary and doesn't move at all. The magnetic field's right there. While the cone itself is a very light material but keeps moving constantly, that B field keeps moving constantly, and the energy losses depend on the area between the hysteresis itself. So the more you can minimize it, the more efficient your speaker is going to be. And to analyze the magnetic circuit within the speaker itself, all magnetic materials are going to be nonlinear. But in this case, we make the linear assumption to simplify calculations and be able to actually analyze it. Looking at a graph that shows the comparison between the magnetic flux and magnetic intensity, you can see that there is either the linear section or the saturation section. The hard part about the circuit analysis itself is to see which part the magnetic core is actually operating in. Use similar Kirchhoff voltage law and Kirchhoff current laws that correlate to the magnetic circuit itself that you would use in normal circuit analysis. And through these, you'll find a load line to see where it crosses within this graph. Where it crosses is the operating point. As you can see, along the comparisons between actual circuit theory itself, you can tell that the load line can be recreated in circuit analysis with electromotive force, current, and resistors. All of these have very similar applications to, say, a transistor, where you have IV curves that look very similar to the curve of the magnetic field of a magnetic core.